and I'm looking at this. What changes at point P because the electron moves? Or the charge moves, doesn't have to be an electron. What do charges produce? Okay, and? You said magnetic field?
Yes.
Okay. And what else do charges produce? I will just, moving charges create magnetic fields.
A force from the electric field?
Oh, it creates an electric field? Yeah, the force requires there to be another particle there. But it creates an electric field also. So if I'm right here, let's just assume Q is positive. So my electric field starts out in that direction. And then when the charge is over here, my electric field is in this direction. I have a change in my electric field, which means there's a change in the electric flux. If I have a change in the electric flux, that's going to create a magnetic field. So right there we have this creation of a magnetic field. Yes, we've talked about a charge moving creates a magnetic field, as was mentioned, but we are now making a bolder claim that the magnetic field is created because it's actually an electric flux that changes. So we start out with a moving charge, and that creates a change in the electric field, which creates a magnetic field. Just as a side note, if I have a charge running across the room, I'm standing right here, I pull out my magnetometer, I'm pulling out a meter that measures magnetic field. Charge goes zipping by. Will I register a magnetic field? Go with your gut. If I have a charge that's zipping by right there and I'm sitting here with a meter to measure magnetic field, will I measure a magnetic field?
Yes.
Okay. Yeah. Why?
Because moving charges create magnetic field.
All right. So now we have this charge creating a magnetic field. Now suppose instead I have a charge moving like this and I'm moving with it. So charge and my meter are all moving together. Will I register a magnetic field then?
No.
Correct. Whether the charge is moving or not depends upon the observer. So you're not always going to register a magnetic field if the charge is not moving relative to you, which to me is one of the really bizarre concepts of all of this. But true story. All right. So I move the charge there, and then now I'm going to move it back. So I move the charge to the right, and then I move it back to the left. So my change in electric field, well, right now I've got a change in the change. So I change it, and then I change it back. So I've got a change in the change, which creates a change in the magnetic field. I am going to stick an extra step in there, which creates a change in the electric flux, which creates the magnetic field. A change in the magnetic field creates a change in the magnetic flux. And a change in magnetic flux creates an electric field. So now, instead of just moving the charge there and back, I'm just going to oscillate it back and forth. I take this charge and move it back and forth, and so I've got harmonic motion going on here. So my change in the electric field is really, I have a change in the change in my electric field, which creates a change in the change in the change in the electric flux, which creates a change in the change in the magnetic field, which creates a change in the change in the magnetic flux, which creates a change in the electric field, which basically creates a change in the electric flux, which creates and the cycle continues. Yes?
All of that still works if it's just one change for all of them. If it's not a change in the change.
You get the cycle going, you need the change in the change. If I just take a charge and I move it to here and I move it back, then you basically are good. And stop, then I kill the process.
Okay. But if it's just going from the left to the right, then there is eventually a change in the magnetic flux and electric field.
If I just move it once,
Yeah.
then there is a change in the electric field that causes a change in the electric flux, which creates a magnetic field. How it's moved from there to there could affect whether there's a change in the change in the magnetic field. Yeah, I guess whether it cycles on forever with just moving it once it would depend upon how the charge was actually moved. And so that's why I'm going through I'm moving it back and forth just so that I don't have to worry about that. So realize what is being produced here is an electric field which creates a magnetic field, which creates electric field which creates a magnetic field, and the only charge that's moving is here, but something else is being produced. And what is being produced here is an electromagnetic wave. And what is an example of an electromagnetic wave?
Charge moving back and forth.
Well, that would create it, but that's not the wave itself. I can give a hint. Does everyone see the board? And we can narrow that down even more. Yes, light, absolutely. This would be called visible light. Microwaves, radio waves, infrared. These are all electromagnetic. So one of the issues, and one of the reasons I mentioned visible light specifically, is that in physics, light could mean everything, or it might mean just the visible spectrum. So we probably should be precise when we use that term. All right, questions to hear before we get into some math, because I know if you leave without doing math in here, you're gonna feel let down. All right, let's do some math. All right, so P is equal to cosine Q. What does the graph look like? Where are you starting with your finger?
I'm trying to think which one's the sine and which one's the cosine. I think it starts at 1.
Okay.
And then it goes down to a number. And so -1.
Yep. Get back up. That's it. It keeps going. It looks like I drew my amplitude a little bit smaller. It's not supposed to be. We would have seen this in the harmonic motion section of, I guess, the harmonic motion day of 151. What's the period of this wave? What's the wavelength of the wave? What do I mean by period?
The time it takes to get to the same spot on the graph.
Okay. More generally, the time it takes to create to do one cycle. What's the wavelength?
The length of one wave.
Yeah. All right. So when I am here, when I get back to where I started, what would be the value of Q here? At what point do cosines start to repeat themselves?
2 pi.
Yeah, 2 pi. And we've talked about it before, I feel confident, but because it's in radians, you don't actually have to say it. Is that the period or the wavelength?
Period.
Why?
It's the time it took to get to where it started to do a loop.
And what's the wavelength? The wavelength, another definition of wavelength is how far a wave travels in one period. So is this representing time or is this representing distance?
Distance.
Pardon? I think somebody said something.
Distance.
Why do you say distance?
Never heard of 2 pi seconds.
Huh. In math class, I have it's usually it's either the period or the wavelength, and, whichever one they're asking, there's no trick questions there. It's, what's the period, then, well, they'll find it the same way that if they just ask what's the wavelength. In this particular case, I didn't give you enough information to know whether it's the period or the wavelength. Because I don't know if Q is representing in essence, I don't know what the units are here. Well, actually, no, that would be radians, but there's a coefficient right in front of the Q of a 1, and I don't know what the units of that 1 is. All right, so let's just keep it generic for right now, then we're going to bring in wavelength and period in a moment. What's the slope of this graph look like? Flashing back to probably the first week or second week of 151. If this were position versus time, then this is what's velocity versus time. How would you find velocity if you knew position? Okay, how does that translate in terms of the graph?
It would kind of look like the opposite of that, like inverted.
No, not quite yet.
Would it be a negative sine wave?
It would be a negative sine wave. All you're doing is taking the slope, because think about delta x over delta t, that's rise over run. So my slope here, what's my slope here?
0.
And my slope here?
0.
And here?
0.
I find it easiest to figure out where 0 is. That's just where the tangent line is horizontal. From here to here, the slope positive or negative? What does a negative slope look like? Right. think I'm. All right, Gina, okay, from your point of view, yeah. So negative slopes go like that. Is this a positive slope or a negative slope? What about from here to here? Okay, so it's negative along here, positive along there, and then starts to repeat itself, and so on. It is indeed a negative sine wave. What about the slope of that? So if this is position versus time, and this is velocity versus time, this would be my acceleration versus time graph. Let's just mark down some points here. So that's pi over 2, that's pi over 2, that's 2 pi, oh, that's 3 pi over 2, 3 pi over 2, pi over 2. So that's pi over 2, pi, 3 pi over 2, 2 pi. All right. So where is that slope equal to 0?
Pi over 2.
And,
3 pi over 2.
all right, from the beginning to pi over 2, positive slope or negative slope?
Negative.
And then from pi over 2 to 3 pi over 2,
Positive.
and oscillates back and forth. That's just the flip of that. This is negative cosine. So we have a pattern here with the trig functions that if I start out with a cosine, the slope would be a negative sine, the slope of that would be a negative cosine, the slope of that would be sine, and then it repeats itself. Questions to hear before I make it look more complicated? All right, as Olivia said, this would be 1 and that would be negative 1. This would be negative 1 and 1. That would be negative 1 and 1. And now to make it look more complicated. If I had y is equal to cosine of 2x, what does that do to it? Okay, this way, all right. So if I've got my graph right here, if that's pi and 2 pi, and pi over 2 and 3 pi over 2, basically it takes it and it squishes it into half the size. You could legitimately think of it as where 1 happened before, I now have 2 of them happening. So there's 1, negative 1, so it happens twice as often in the same either period or wavelength, depends upon which one you're talking about. All right. What does this do to the slope? How would you compare this to this? Okay, matter of fact, it's twice as steep. So my graph, if I did the slope of that, I'd have, I'll just call it y prime, is equal to, well, cosine becomes negative sine, that 2x stays the same, but now there's a 2 in front. So that's 1, that's 2. negative 2. What about the next one? Suppose I wanted the slope of this. What is the slope of this compared to the slope of that?
-4 cosine 2x?
Yes. So we did the slope of it. It's 4 times what it was before because we got this 2 here, but we also have this additional 2 here. So negative 4 cosine 2x. And my drawings are going to get worse and worse after that. Fortunately, we don't have to draw lines. Keep drawing these curves. All right, so if I got a number right in front of my variable there, it just takes the slope in it. In essence, you just multiply by that, whatever that is. So if I had y is equal to cosine of 5x, the slope of that would be
-5 sine
negative
5x.
and then the slope of that,
-25 cosine 5x.
yeah. If y was equal to 3 sine of negative 4x, what would the slope be? Have you had calculus?
Yes.
Okay. That's okay. This was just so brilliant that you picked it up.
I mean, negative, I believe there's a sign.
Say it again?
Thinking out loud.
Okay.
-12 cosine 4x.
All right, so you multiply